So after just say, I will present my work with Raph and Jean-François that I started with them a year and a half ago. So the presentation is entitled A Research Heuristic for Stochastic Production Distribution Planning with Transportation Mode Dependent Lead Time. So I will begin by presenting the problem, the solution method, some experimental results, the extensions that we just start to work on, and finally, I will conclude. So the problem. So it's a stochastic production distribution problem with lead time. The idea is that we have one facility, multiple customer or retailers. This setup can be quite general. Each of them have an inventory. The retailer face an unknown demand, so the stochasticity comes from here. And in between, we consider multiple carriers. So for example, a transport by plane, just depicted by a plane, will be very fast, but also very expensive. And on the contrary, transportation by ship will be much slower, but also very cheap. So that's the basics of the problem. Of course, So to summarize, the stochastic production distribution problem with lead time. So we have to manage production setup and production quantity at each period of the time horizon. We have to manage the inventory at the facility and at each retailer. So it's an integrated problem. At each period, we have to choose any number of transportation mode, and we have a setup cost for each of them. And then we have to decide on how much we send to each customer. And as I said, each retailer faces a stochastic demand, and we don't impose any distribution on each of them. We don't want to impose that the distribution is the same for all periods, that it's a that it's a very well-known production distribution, like a normal distribution can be anything. And very importantly, it's a multi-stage dynamic problem. So multi-stage because we have multiple periods, and at each of them, the demand is revealed, and we can adapt the production and the transportation to the revealed demand. Of course, some related problems have been studied in the literature before. The closest one is the one warehouse multi-retailer problem, in which we find the facility, the retailer. The retailer have a stochastic demand, and we manage the inventory at each of them. But in the one warehouse multi-retailer problem, there is only one transportation mode. And most of the time, it has a lead time of 0. So it's much simpler because we can produce and send to retailer at the same period. We also have the production routing problem. And in these problems, we don't necessarily consider back and forth to do the shipment to the retailer, but complex routing with capacity constraint and so on. So it's more complex, but the methods that work for this problem focus much more on this routing part. So they are not very suited for our problem. And in this case, the lead time in terms of period is also of 0 because the trucks typically perform their tour in 1 day. So it's a lead time of 0 in our case. And we also have the dual sourcing problem, which is quite the opposite problem of our case, because we manage one inventory of one retailer facing a stochastic demand, and this retailer can call for multiple facilities, of which we don't manage production on stocks and so on. The question is more on from which facility we want to get resupply with different costs, setup costs, unit cost, lead time, and so on. So we find all these elements of our problem, but with only one inventory to manage. So that's the difference. So to summarize the literature, so we have the one warehouse multi-retailer problem, the production routing problem, and the dual sourcing problem. So we have problems that manage all production, transportation, and inventory, but they usually have only one mode and with lead time of 0 or constant over all the horizons, which is not assumed in our case. And for this problem, we have policies or MIP, but they don't scale very well for our case because the MIP becomes very large, even for small instances. So CPEX does not work for this problem very well at all. We also have the PRP, in which, as I said, the lead time is almost all the time 0. And we have very efficient methods for this problem, but they focus on the routing problem. So it's not what we are interested in for all problems. So this method, we can't really use them. And for the dual sourcing, they manage transportation and inventory very well. And with a mode, either 1 or 2, I didn't find any dual sourcing problem with 3 modes, because most of the time they use policies with an analytical formula to decide on when to order from which supplier and so on. So with 3 modes, this formula become extremely complex, and with lead times that vary over time and distributions that vary over time, it's completely unmanageable. So again, we can't really use this method. So because we want a method that can take into account any number of transportation modes with any lead time, and we want to be able to consider any probability distribution of the demand. So I will go a bit into the detail of how we will present this problem, or we want to solve it, or we want to consider it. So first, the decomposition of a period. So I have the previous period, the next period, and let's say we stand at period T. So at the beginning of the period, we decide on production, so production setup and production quantity. Then we decide on transportation, so which retailer will be resupply, with which mode and how much will be sent. Then the demand is revealed at each retailer, and we compute the inventory and possibly lost sales if the inventory would be 0. And then we move to the next period. So again, we decide on production, transportation, and we receive the goods that were sent during the previous period. Okay, it's only a lead time of 1, so that's from period T to T plus 1. And again, we reveal the demand, compute the inventory, and we move to the next period. Is it clear? Okay. So because it's a multi-stage dynamic problem, we use a rolling horizon framework to reduce its complexity. Otherwise, it's completely unmanageable. So for each period, we fix what takes place before. We sample possible demands for the few periods to come. And we take decisions on the period at hand. So for this one, we take the decision only for this period. Then the demand is revealed, and we compute the inventory, as I said in the previous slide. Then we move to the next period. So we have a step of 1 in our running horizon, and we do that for the whole horizon, day by day. To sample the possible demand for the periods to come, we use a scenario tree. So we see here the periods that were in the past. Because they are fixed, there is only 1 node because we know the demand. And then for the period to come, we sample multiple possible demand. And we hope that if we find a good solution for all this possible demand, it will be good for the real demand that we will know at the end of the period. So that's how we represent uncertainty. It's called scenario trees. And here's a model that we solve. So at each period, we solve a multi-stage static dynamic model. Static dynamic means that we impose that the production setup and transportation setup are the same for all scenarios. So here, the Y represents the production setup and the Z represents transportation setup. They are not indices on the node, but on the period. We impose that to reduce the size of the problem. And then we have to decide on the production quantity, transported quantity, the inventory, and the lost sales. Then the constraints are quite standard. And we want to minimize the cost, the average expected cost over the scenario tree that we use to sample the possible demand for the periods to come. So now I will go to the solution method that we developed to solve the model that I just presented you. Before I start, is there any question on the problem?
Can you go back on slide?
This one?
Yeah. What does it mean the summation of n in n t minus 1 is the?
Oh, that's a little trick to model the fact that we take the decision about transportation and setup before we know the demand.
Okay.
So that's how we model it. And then when the demand is revealed, we compute the inventory and the lost sales without this -1 to say that we do it after we know the demand.
Okay.
Yeah.
Performing all modes of transportation are possible for every demand, right?
For every retailer. Yeah, and we don't impose any capacity restriction, so we can send any amount of.
Just based on the inventory and the cost of the transportation, right?
Yes. Okay, so for the solution method, I will first speak a bit about the existing method in the literature. So to solve this kind of problem, many papers talk about dynamic programming. So they have one state for each node of the tree search and any state that our whole system can be in that node. So it works usually fine, but in our case, it does not at all because it does not scale with the number of carriers and the lead time. Because when we model the state of our system, we have to take into account all the amounts that are in carrier at the moment. For example, in our instances, then things with the ship take 4 time periods. So we have to account for all goods that are currently in ships, and it's continuous demand. So dynamic programming does not work at all. There is way too many states, and we did not have any idea to reduce that number of states. And also, dynamic programming usually work on the fact that the decision that we take at the beginning of the time horizon have a strong impact of all the time horizon, that we can really restrict the decision depending on the first stage decision. In our case, the first stage decisions are not that important because we take decisions about production and transport at each period. So how many we send and produce on the first period over 14, 15 days is not really important, not enough to restrict the decision about the whole time horizon. Also, we can use branch and cuts. So typically Cplex with other cuts or other branching method. But in our case, we completely abandon this, this idea because of the size of the scenario tree to sample all the demand, especially because we use lead time, which are positive and typically a bit large. We need to sample the demand over many periods. So we do it over 8 periods in general in our experiments. So it requires a large scenario tree that Cplex cannot handle. So we dropped this idea, but one thing that we noticed during our preliminary experiment is that when we fix the production setup and transportation setup, it's only a linear programming, which is of course way easier. And also, when in the running horizon, when we move from one period to the other, this binary variable does not change that much. So we can reuse the solution from the previous period and to adapt it to the demand that was just revealed. So now I will go to the method that we developed. It's a tree search heuristic. And we based it on limited discrepancy search. The idea of this tree search method is to take a reference solution. So here, the binary variable from the solution of the previous period, and branch on binary variables. So for each of them, we have 2 choices. Either we take the value from the reference solution, or we take the other choice. We'll continue to do that, but we forbid to have too many differences compared to the reference solution. Here, in this example, we limit number of difference to 2. So in this example, we have 1 difference, 2 difference, and the third one is forbidden, so the node is not created. So this first method limits the width of the tree, the number of nodes, and we assume that it's reasonable to do so because we notice that the solution does not change very much from one period to the other. So in this example, it's a very small tree, so it does not prune that many number of nodes, but in practice with 15 periods, so we have 50 retailers, 3 carriers per retailers. The tree is much larger, so we prune many nodes thanks to this technique. But even if we prune nodes, it's not possible to explore the entire tree search. So we use a second method called anytime column search. So this idea is to divide the tree search that I presented just before in columns and to explore it column by column. So in the example, oh, sorry, it's a bit below, but here the column width is 1, but we can choose any width. So we generate the first 2 nodes as previously, select the most promising one. I will present the heuristic that we use to select the most promising one just after, and we expand only this one. And we continue at each level of the tree, we expand only the most promising node. Yeah. And when we reach the bottom, we go back and we do it again. So column by column. And if we have enough time, we will explore the entire tree search. But if we don't, which is very likely, we will focus on the most promising node and in the hope to obtain good leaves, which represent good solutions. Now I have to focus on the method, so the guide heuristic that we use to determine if the node is promising or not. And to do so, we have to estimate the cost to go. Because if we take this node, we have the decision for the first 2 variables, but not for all the other variables. So we need to estimate what these 2 choices could imply for all the other variables and estimate what will be the cost of the solution at the end. To do so, we use a flow-based heuristic that uses a time-expanded network of our setup. So we have 1 source, 1 sink, 1 copy of the facility for each period, 1 copy of each retailer for each period. This arc from the source to the copies of the facility represent production. And this arc from copies of the facilities to copies of the retailer represent transportation. Here, because the lead time is 4, we have an arc from the copy at time period 1 to the copy at time period 5. And then we have the demand that is represented by the arcs from the retailer to the sink. But in our problem, the demand is a node. So if we would like to consider the demand as unknown in this problem, we have to duplicate all these arcs, but then it's not exactly a flow because the flow will split and so on. It's called a generalized mean flow problem, but it's very hard to solve. So we don't want to do that because this guide heuristic will be called many, many times in the heuristic. So it needs to be very fast. So to do so, we aggregate all the scenarios. And what we want to determine with this flow-based heuristic is how we can edit the reference solution. So one we take from the previous iteration to adapt it to the decision that we just made and to estimate what will be the cost of the solution at the end. So to be more clear, here is the MIP model. So we have all the variables that we add in our multi-stage static dynamic MIP, but we are only interested in the modification of them. So they can be either negative or positive. Here is the produced quantity, so xt, so that's the modification of the production at period t that will be applied to all the scenarios. So at period, so for all the scenarios at period t, so for all the xn taking place at period t, we will apply this xt at. But we want the solution at the end to be feasible for all the scenarios. So we have to bound this modification. So for all the variables, we compute by how much we can reduce it, the maximum reduction possible for all the scenarios, and the maximal increase for all the scenarios. Then it's usual constraint for a problem, and it's a minimization problem because we want to reduce the cost of the solution as much as possible. So when we take a decision, we solve this problem. So we modify a bit the bound here depending on the binary variable that we changed. We solve the problem, we get this, this modification of all the variables, and we have an estimate of the cost of the solution with the modification that we just considered. It's an estimation of the cost to go. It's not the true one, but we can guide your heuristic with that. So is it clear about this, this guide heuristic that try to improve solution to estimate the cost to go? Okay, so I will move to some experiments. So first about the instances. Because our problem is quite close to the one warehouse multi-iterator problem, we use instances of this problem from the literature. And we consider instances with 50 customers over 15 time periods. We have 3 transportation modes with the lead time of 1, 2, and 4. For the simplicity of our instances, this lead time are constant over all the period. And we have a cost of this of each of these carriers. For the fastest one, it's equal to the cost used in the instance of Soliali and Seurat. So this one, we represent it with a plane as air freight. The one with the lead time of 2 and a cost of half the original cost, we represent it with a truck for road transportation. And when the lead time is 4, we divide the cost by 3, and it's represent transport by ship, so by sea. But it's all synthetic data, it's all made up just to test the method and to understand a bit how it works. The coefficient of variation of the demand is of 30%. So if the original demand is of 100, it's likely that the demand in practice will be between 70 and 130. And for the parameter of our method, we limit the modification of the production variable to 2. So typically, we drop one binary variable and we switch it to another period. We limit the modification of the transportation variable to 2 times the number of retailers. So a bit of the same idea, but for each retailer. And for the width of the column, at the beginning, we consider 20 nodes in our tree search. And at each iteration, we'll consider 5 more. So 20 for the first one, 25 for the second iteration, and so on. So we'll explore quite a lot of nodes with this method to browse solutions. So first evaluation of the proposed method. Okay. So just to give you an idea, for the 50 customer instances, we give 300 seconds to solve the static dynamic multi-stage model. In general, it takes a negligible amount of time to evaluate a node. So we succeed in making our guiding heuristic as fast as possible. And on average, we will explore a bit more than 300 solutions. So we have 300 leads that we evaluated. So 300 complete solutions on which we will select the cheapest one, of course. But the first approximation that we did in our method is the rolling horizon. At each period, we will sample the demand for the periods to come. And there is multiple ways to sample the demand. So in our method, we sample 8 possible demand for each retailer for the first period, 4 for the next 2 periods, and 2 for the last period. And then we use the average demand for the period that comes after. We use 8 at the beginning because that's the most important decision. That will be the one that will be fixed after. But we can say that it's better to sample less demand to go faster and to explore more solutions, or to sample more to have a better solution, but the problem will be harder. So for all class of instances, so with dynamic demand and dynamics fixed setup cost, or for static demand, static fixed setup cost, it's a bit of all the same results. So I will just detail the average. So we see that when we sample less, the cost is higher than when we sample like average way, because we take decisions that tend to be less robust, and it's not much faster. On the contrary, when we sample more, the cost is again higher because the problem is much harder, so we don't have enough time to browse that many solutions and take a good and find a good one. So this parameter is not that sensitive, but it needs to be experimental to take a good decision on this parameter. Contrary to the one for the tree search parameters that are way more flexible. And we also compare our result to Cplex. So mind that we give 1 hour to Cplex compared to 300 seconds for method, but Cplex can never prove the optimality of its solution. And in average, our solution is 17% better because the gap to optimality that Cplex have is usually between 20 or 30%. So it's really failed to converge and it doesn't find good solution at all. So the comparison to Cplex on the whole static dynamic multi-stage problem at each period is a bit pointless. It cannot really give you hints all the method except that we are much better. And we can also use Cplex to guide the tree search. So at each node, instead of solving the flow problem that I present you, which only estimate the cost to go, we can use Cplex to get the real cost to go. Of course, it's much, much slower, in average 500 times slower than heuristic. And we can notice that our cost to go estimation is not that good. It's already 9% off, 9% higher than the real cost to go estimation. But at the end, it's able to find really good solution, which have a gap to the one identified by Cplex way below 1%. So that's the main takeaway of our method. We can use a very heuristic estimation of the cost to go estimation to find good results. The important thing is that they are correlated. If the real cost to go is high, then the estimation will be higher. Even if they are way off, this correlation is an important thing. Now I will present a bit the detail, with the detail on our instance to just give you an idea of how it would behave in practice, even if all that are all synthetic. So first is, so we solve the instances with different coefficient of variation of the demand. So 0% is deterministic, 30% is what we consider for now, and 90% is a very, very uncertain environment. And for each of these setup, we solve the instances with all carrier with sampling, so with the scenario tree, or without sampling, so we solve the problem on the the average value at each period. Of course, when it's a deterministic problem, it doesn't make any sense to do sampling. And we solve the instances with all carrier or with only one carrier at each time. So only the plane, only the truck, only the ships, even if it's all made at name. And we also evaluate the value of stochastic solution. So that's the gap between these two values. So how much is it important to sample the possible demand for the periods to come, contrary to take the decision based on the average demand? So first, we can see that when the uncertainty increase, the cost increase, that's expected. And also we can see that the value of stochastic solution is more important when the uncertainty is more important, which is also expected. But what's interesting is that the value of stochastic solution is much higher when all three carriers are used simultaneously than when only one carrier is used. So in our case, when we want to combine all carriers, it's very important to do a sampling of the possible demand instead of just solving the deterministic problem, which is way easier. Second, we present the repartition of the cost when different combination of carriers are available. So this column represents the combination of all three carriers, only two of them and only one of them. And we separate the production cost, the storage cost, transportation cost, so both fixed cost and per unit cost, and the lost sales. As expected, the cost is the lower when all three carriers are used. And what's also unexpected is that when we use only the plane, of course, the transportation costs are very high, but there is also a lot of lost sales, which is a bit counterintuitive because we can be very reactive with only a plane. But the plane is so expensive that it's often just simpler to just lose the demand instead of serving it. And we can also notice that there is a very small difference between the combination of ships and road transportation compared to the addition of the plane. It's because the plane is only useful in very specific situations, in very unexpected scenarios, unexpected realization of the demands, and the plane can be used to efficiently resupply one customer, but it's quite hard that we will resupply the same customer twice with the plane during the whole time horizon. So we have the detail here of how many times we call each carrier during the whole time horizon, and how much quantity does it transport. So I just told you the plane just transports very, very few items, and it's called quite rarely. And also, as expected, when we have all three carriers, most of the goods are carried with the slowest mode, the cheapest mode. And we just combine it with ground transportation to adapt a bit to the scenario on the fly, and maybe to smooth a bit the production over the period. Sometimes it's a bit easier like that to not pay the fixed production costs too often. So do you have questions on the experiments, about the method, about the application example?
Sorry, I missed how did you cope with the uncertainty?
You mean the scenario trees?
No, in a model. You use
So at each period of the warning horizon, we sample possible demands with a scenario tree like that.
You use scenario-based?
Yes, but the demand that will take place typically is not in the scenario tree because it's continuous demand. So we just want to take a decision which is robust for many possible demands, then take the decision, and then we learn the demand.
How did you predict the probability of the scenario?
They are all equivalent. We sample. So for example, for the first period, we sample 8 possible realizations of the demand, and they have all the same probability.
How do you generate the demand, and how do you impose the variability, the level of variability? Do you follow a probability distribution for the demand?
In our test instances, it's a normal distribution for each customer at each period. So we use the mean of the normal distribution will be the average expected demand used in the instances. Okay, so we use the instance of Soliali and Surreal for the one warehouse multi-retailer problem. It's a deterministic problem. So each retailer at each period has a demand that will be the expected demand in our case. And then the standard deviation of the normal distribution is 30% of this average demand, or 90% in the extreme case. And that's how we sample realizations.
how many scenarios from demand realization?
So for each instance, we solve it 16 times with different realization of the demand. And at each period in the time horizon, we do 512 scenarios, I think, for 4 times 8 times 4 times 4 times 2 times 2. I think it's 412. Yes?
I'm not sure if I did right, but your fleet is on capacity, right?
You
didn't capacity on your fleet.
No.
So what's the application? I mean, because sometimes it's not possible to use ships and trucks because sometimes it's not available to use to deliver. I mean,
maybe some transportation model is not available.
yeah, exactly. Because sometimes it's not possible to ship your products with trucks. So how do you consider that?
So our instances are quite simple on that regard because it's all the same carrier for all the retailers. But if you want to have some differences, then you can just put an astronomical cost to road transportation to one retailer to say that it's not possible. And then it will simply never be used.
Yeah, so you consider cost, but on the other hand, you don't consider capacity because like planes have much less capacity than trucks or ships.
Yeah, for now we don't, and that's the first slide of the extension. Yeah, because it's a bit unrealistic to ask for the plane to transport a large quantity, even if it never happened in our instances. It's better to have the constraints.
I mean, for rapid response, but in general, we always ask for planes to deliver.
So it will be, I don't know if you consider the economies of scale, because the cost, the transport cost might vary with the volume, you know?
Yeah, but
specifically for chips or.
Yeah, it would be interesting to consider that too, but it's very hard then to consider the economy of scale. So maybe I will do it if I have time, but all this method will completely fail if we consider the economy of scale because the cost on the arc will be piecewise linear at best, or even more complex representation. And then it's not a simple flow, mean cost flow capacity problem. It becomes much harder, and then I don't know how the research will behave and so on. So indeed, it will be very interesting, but very challenging question.
Yes, that's just. How do you consider applying pandas? Like, I noticed that the setting state of the problem is video program.
It's multi-stage problem, so each stage considered to.
I mean, the first one, you don't have any binary or integer variable in your next stage. After yours.
Problem.
Once your setups are fixed, then you have, as you explained, a linear programming
Yeah.
problem. So I think as an alternative, the question is as an alternative, given the idea that if these things are fixed, then you have a linear programming problem, can you use benders as well?
But, it's kind of like L-shaped, and you can consider and you can cope with the scenario.
Yeah, we could try indeed the L-shaped method, but because of the size of the scenario tree, I don't know exactly how it would behave, and I didn't try it. It would be interesting, but to have a better baseline comparison to CPLEX, for example.
Yeah, exactly.
But no, I didn't. Sorry.
Which language do you code?
C++.
Okay, and how do you solve the sum problem? Which solver do you use?
For which part?
For some for your sum problem. You just mentioned your your method is better than simplex?
So the tree search is coded using a library called CATS, which is developed at Bordeaux by the University of Bordeaux. And for the mean cost flow problem, I use a library called Lemon. I don't remember where it's developed, but it's also a research project. And both of them are very efficient to do what they are meant to do. They are not that general tool. That's also why it's way more faster than Cplex to solve the guide, to guide the research.
Thank you.
Okay, so I will move to the extension that I started to work on about 2 months ago. So we want to generalize the transportation mode. So first, to have a capacity constraint on the transport, to have a cost per containers to model the fact that it's more expensive to ask the plane to transport a lot of goods. And we want to have different capacities depending on the mode to model that a ship is way larger than a truck, which is way larger than a plane. And we want especially to work on stochastic lead time, because for now, if I say that the plane take 1 day to do the delivery, it's always 1 day. And for the ship, it's always 4 days, but it's far from the truth. It's not as well known in practice. So we want stochastic lead time in our problem, but that especially this second part complexify a lot the problem, because we have to sample 2 types of uncertainty, so the demand and the stochasticity of the lead time. But in our modeling of the stochasticity of the lead time, we say that we know the lead time. So when we are at period T, at the beginning of period T, we know how long it will take us to reach every customer with every transportation mode if they are called on that period. So at the beginning of the period, we learn the lead time, and at the end of the period, we learn the demand. So we kind of have to multiply the 2 lead times to have first the branch on the lead time, second the branch on the demand. Otherwise, the algorithm would just deduce the demand based on the lead time that we gave him. So we have to do this, which even increase the size of the scenario trees, which was already quite large. And because we have a const per container, it's not a binary variable for the setup decision on the transport, it's an integer variable. So the size of the tree search also largely increased. So we have to work to consider these 2 extensions. And we did a bit of preliminary experiment on this, first with Cplex, but Cplex really failed on this. We had to reduce a lot the sampling of the demand. So before we were sampling 512 scenarios. Now it's already 8, 16, 32 scenarios on the demand, and only 8 for the lead time. Otherwise, it takes too much memory for Cplex, and Cplex already uses 55 gigabytes of memory and takes 3 hours to try to solve the problem, and of course, never reach optimality. So that's why we started to adapt the tree search heuristic that I developed previously to have a baseline solution. But to do so, I had to adapt the guide heuristic. And now 1 arc between the facility and 1 retailer does not represent 1 freighter, but represents the minimum cost to do this transportation between these 2 time periods on all the scenarios weighted with their probability depending on the lead time. So it becomes very imprecise, because to do some movement, we would have to pay, for example, the setup cost for the truck in 1 scenario and the setup cost for the ship in another one to do this transport from period 2 to period 4. But our research branch on 1 variable at a time, so it cannot do that. So the cost to go estimation even lost its precision. It was already not so good, but it's even worse now. So we fear that it will not be able to find good solution at the end, because it starts to become really imprecise. And yeah, if we so the idea that we have to circumvent that is to work with Monte Carlo tree search. So instead of building one scenario trees at the beginning, we will generate the scenarios on the fly to evaluate solution. And the more promising a solution seems, the more scenario we will generate to evaluate the solution to refine our estimation of the cost of this solution. And to browse the state space, we plan to use HOO, so hierarchical optimization. We have a small drawing here. So at the beginning, we will sample a bit every possible combination of the transport and production. And then the algorithm focus on the most promising one to really determine on how much we would send to every retailer with each of the transport. But what we fear is that for this initial sampling, we have way too many combinations. So we'll have to use tools from Bayesian optimization to kind of interpolate results from different combinations of the binary variables. So we have to work on this. It's very preliminary, but we have idea to solve the problem with stochastic lead time and cost per containers. So to conclude, we first, with the stochastic production distribution planning with lead time, we extend the already well-known one warehouse multi-retailer problem with multiple transportation mode and with lead time, which is very important, the lead time. We propose a tree search heuristic method to solve the static dynamic multi-stage problem at each period of the rolling horizon. And we show that we can use an imprecise cost-to-go estimation to quickly guide the tree search to a good solution. And we show that it's very important to solve the multi-stage problem on the scenario tree at each period, especially when we have multiple transportation modes with lead time. Otherwise, if we just solve the deterministic problems, the solution will not be very robust to many realization of the demand. And as I said, we are now working on stochastic lead time and the extension to cost per containers. Thank you very much for your attention. And if you have more questions, I will gladly answer it.